So here we look at our general antidifferentiation rules. So the first rule is called our constant rule. So if we let k be some arbitrary constant value, then the integral of constant k dx is equal to that constant k multiplied by x plus c. So any antiderivative of a constant is always that constant times x plus our arbitrary constant c. Next is our power rule. So if we let n be a real number not equal to -1, then the integral of x to the n dx is equal to x to the n plus 1, all divided by n plus 1 plus c. The natural exponential rule, so here we should go ahead and let k be some real number, again a constant value. If I have the integral of the natural exponential raised to the kx dx, this integrates to the natural exponential raised to the kx, all divided by that constant k plus c. We also have a common exponential rule. So here we let a be a real number greater than or equal to 0 but not equal to 1. And we have a exponential base a raised to the kx. And so when we integrate this, we're left with that exponential base a raised to the k times x divided by k multiplied by the natural log of a plus c. And then last but not least here with our general rules, we have the natural logarithm rule. So this is the case where we have n is 1. So if we have the integral of 1 by x dx, this integrates to the natural logarithm of the absolute value of x plus c. Next, we'll go ahead and explore the general antidifferentiation rules for the trigonomic functions. So here we look at the 6 basic antiderivatives for our trigonomic functions. So again, we're going to let k be some constant value here. So if we have the integral of sine of kx dx, this integrates to minus cosine of kx divided by that constant k plus the arbitrary constant c. We have the integral of cosine of kx dx. This integrates to sine of kx divided by k plus c. So we can see how the antiderivatives here are the reverse of our derivatives. The third case here, if we have the integral of secant squared of a constant k times x dx, this integrates to tangent of kx by k plus c. If we have the antiderivative of secant of kx times tangent of kx dx, we think to ourselves, hey, this is the derivative of secant. So the antiderivative of this is secant of kx divided by k plus c. We have 2 more to go. If we have the integral of cosecant squared of this constant k times our variable x dx, again, we think to ourselves, that's the derivative of a negative cotangent. So here is our antiderivative, minus cotangent of kx divided by k plus c. And last but not least, if we have the integral of cosecant of kx times cotangent of kx dx, this antidifferentiates to minus cosecant of kx divided by k plus c. So now that we've seen the antiderivatives for our 6 basic trigonomic functions, we need to now look at the general antidifferentiation rules for the inverse trig functions. So rule number 7, we look at the antiderivatives for the inverse trig functions. And what I'm going to do here is give you 2 alternatives for each case. And the first rule I give you is going to be the one that we use more in Calculus 1. The second one is going to be one that we begin to use later on in Calc 2 and for the rest of our mathematical lives. So here we go. the first antiderivative rule. For some constant k, any real number k, if we have the antiderivative of 1 by the square root of 1 minus kx squared dx, we look at this antiderivative and we think, what inverse trig function does this look like? And it looks like inverse sine. So this integrates to inverse sine of k times x divided by k plus our arbitrary constant c. The second rule, we have the general antiderivative of 1 by 1 plus kx squared dx. Again, we think to ourselves, which inverse trig function does this look like? And this is inverse tangent. So this is inverse tangent of kx divided by k plus c. And then last but not least here, we have the integral of 1 over x multiplied by the square root of k times x squared minus 1 dx. And this integrates to inverse secant of kx plus c. And this is where k times x is strictly greater than 1. Now, these are the more general antiderivative rules for our inverse trig functions. They match our they match our differentiation rules, so they're easier to recognize. However, we don't use these as frequently as we use the following forms of each definition. So looking back up at case 1 here, in addition to this form, we may also see the integral of 1 by the square root of k squared minus x squared dx. And this antiderivative is defined as inverse sine of x divided by k plus c. So this is an alternative, a more generalized form of the antiderivative for inverse sine. In case 2, we can alternatively see the integral of 1 over k squared plus x squared dx. And this antidifferentiates to inverse tangent of x divided by k, and that's all divided by that constant k plus c. So again, this is that more generalized form. And then last but not least, we also have a generalized antiderivative for inverse secant. So this is 1 by x multiplied by the square root of x squared minus k squared dx. And this antidifferentiates to inverse secant of the absolute value of x by k, all divided by k, plus c. So for now, we can use the original forms of these antiderivatives, but as we progress through our integration techniques in Calculus 2, we end up using these 3 new forms more frequently, especially with trig substitution. Last but not least, we have 2 properties of antidifferentiation that we want to explore before we begin practicing. So the first property, actually both properties, are going to look familiar here. We have equivalent forms of these properties in algebra, in pre-calculus, and differentiation, the constant multiple rule, and the sum and difference rule. So starting with our constant multiple rule here, let's go ahead and let k be any real number our little hearts desire. So it's some constant value. So if we have the integral of a constant k multiplied by some function f of x dx, to make this integration or this antidifferentiation process easier as we begin, we can pull that constant k to the outside of the antiderivative. So this becomes k times the antiderivative of f of x dx. And when we antidifferentiate, we end up with constant k multiplied by that antiderivative capital F of x plus that arbitrary constant c. With the sum and difference rule, we should let, and this should go for case 1 as well, we should let f and g be continuous and differentiable functions on some open interval. So if we have the integral of a function f of x plus or minus some other function g of x dx, again, to make our integration process easier as we begin, we can separate this to the sum or difference of two antiderivatives. So this becomes the integral of f of x dx plus or minus the integral of g of x dx. So looking at a large antiderivative in little pieces one at a time can make this process substantially easier as we learn. And then we can integrate or antidifferentiate each piece individually. So the antiderivative of little f of x becomes capital F of x. The antiderivative of little g of x becomes capital G of x. And then don't forget here we need, of course, that arbitrary constant plus c. So we're now ready to begin practicing these rules.